On this example, we want to find the x-intercepts of the graph without graphing the function. So we're looking for x-intercepts for this function f of x equals the square root of x plus 32 minus the square root of x minus 4. So if we're looking for x-intercepts, we're going to let y equal 0. I don't see a y in this equation, so what we have to remember is that f of x is the same thing as y. So we're going to let f of x equal 0. This gives us the equation 0 equals the square root of x plus 32 minus the square root of x minus 4. So this equation is a radical equation or a root equation. And when you solve a root equation, the strategy is that you want to eliminate the roots, eliminate the radicals first. And then once you eliminate those roots or radicals, then you could proceed with solving the equation. This example actually has two different roots or radicals, and it makes the process even longer because you can only eliminate one root at a time. So what we're going to do is we're going to start by choosing one of those roots to eliminate, and I'll add square root of x and add 4 to both sides of the equation. So when we want to eliminate a root, you want to isolate that root. So I've isolated the square root of x plus 32. By adding square root of x to both sides and adding 4 to both sides, I've isolated that root. And then you want to eliminate that root. And you eliminate it by doing the opposite operation. This root is a square root, so the opposite operation is squaring. I'm going to square the left-hand side and square the right-hand side. The square root and the square cancel each other out just like we planned. That eliminates the square root of x plus 32. And on the left-hand side, we've got a little bit of algebra cleanup to do. So we're going to square means to multiply it twice, so that's square root of x plus 4 times square root of x plus 4. Let me come over here with some more space. And we're going to start to multiply that out. Square root of x times square root of x is x. Maybe I'll write it out in detail for you guys. I have square root x times square root x plus 4 times square root x plus 4 times square root x. And 4 times 4 is 16. And on the other side of the equation, we have x plus 32. Square root of x times square root of x is square root of x squared. These two terms in the middle are like terms or like radicals. So when we combine them, we add the coefficients. That becomes 16. No, 4 plus 4 is 8. So that is 8 square root of x plus 16 equals x plus 32. Square root of x squared is x. Okay, we've done a lot of work already, but we've only met our first goal of eliminating that radical. We still have a radical in our equation, so we have to repeat that process over again. So you repeat the process over and over again until all the radicals are gone. So let's subtract x on both sides and subtract 16 on both sides. That gives 8 square root of x on the left, and on the right, x minus x cancels out the x. 32 minus 16 becomes 16. I'm still trying to isolate that radical, so I'll divide both sides by 8, and that gives square root of x is equal to 2. 16 divided by 8 is 2. Now to eliminate that radical, we want to do the opposite operation. The opposite of square root is to square. The square root and the square cancel each other out, giving you x, and 2 squared is 4. So we have a solution for our x-intercept, but we want to check it. There's always a possibility when you square both sides that you get what's called extraneous solutions. So we want to check to make sure that this really is an x-intercept by substituting it into our original equation here and make sure it comes out true. So let's give that a try. So we have 0 equals the square root of 4 plus 32 minus square root of 4 minus 4. So 0 equals the square root of 36 minus the square root of 4. The square root of 4 is 2 minus 4. The square root of 36 is 6. 6 minus 6 does give me 0, so I can check this off that this actually is an x-intercept. It's 4, 0. So this radical function has an x-intercept at 4. So on this question, we're given a graph, so you can see this picture here, and we want to determine the domain and range of the function. So before we look at that picture, let's just remind ourselves domain is going to be the set of first coordinates for the x's, and the range is going to be the set of second coordinates or the y's. So we want to use this picture to help us determine the domain and range. Now this picture is a little bit confusing, especially at this time in the class. We don't have a lot of experience with this type of graph. As we move forward in the class, we will get a lot more experience with these types of graphs in Chapter 4. This is a graph of a rational function, and it has some features that are new to us. So you see these vertical dashed lines and these horizontal dashed lines. Well, there's only one of those. These are called asymptotes. And this is a feature we'll study in detail later. These asymptotes are places where the graph is getting closer to that line without ever reaching it. So in our picture, we're going to use them as guides to where the line is going. So for instance, this curve is getting closer and closer to this vertical line without ever reaching it. So it gets closer and closer and closer without reaching it. This line is getting closer and closer and closer to this horizontal line without ever reaching it. So those are like fences, and your line is not going to cross the fence. So when we're looking for the domain, the way that I like to do it is to get out a ruler, and if you don't have a ruler, just use a pencil. And you're going to hold your pencil vertically, and you're going to go from left to right. We go from left to right because we want to go from smallest to largest. So we start with domain, and we're going to find our lowest x value. Our lowest x value, where what I mean by that is to find our lowest x value, we're going to look at where our ruler or pencil is touching the graph. So this line is going on forever here. So that means that even if I keep going further and further to the left, my ruler or pencil will still be touching the graph. So that means that my domain is going to start at negative infinity. So then pay attention to if you're touching the graph. I'm touching the graph all along here, and then I get to this line. And remember what I said about these lines. This is going to keep going closer and closer, but never reach this vertical line. So since it never reaches that vertical line, we know that the ruler is not touching the graph at that vertical line. So your domain stops at that vertical line. So -4 is not part of your domain. But right after that line, you see this portion of the graph is going to get closer and closer without ever reaching. And so right after that line, your domain starts again. I'm touching the graph all along this section, and I stop at the vertical line. I stop at the asymptote. Right after the asymptote, the line, the graph starts again. And so your domain goes from 4 to infinity. So just to repeat, I'm touching the graph all along this section. This section goes from negative infinity to -4. I'm touching the graph through all of this section, which goes from -4 to 4. And I'm touching the graph all of this section from 4 to infinity. So that gives us a domain of negative infinity to -4, union with -4 to 4, union with 4 to infinity. So then for the range, we want to look at the y value. So I'm going to hold my pencil horizontally, and I'm going to go from bottom to top. And notice down here at the bottom, I am touching the graph because these arrows go down forever. So my range will start at negative infinity. I'm touching the graph all the way until right here at a y value of 0. So my range will start at 0. Excuse me, stop at 0. Now on this 0, this point right here is on the graph. That's the origin, 0, 0. So 0 is a part of this graph. 0 is a part of this range. So we want to use a bracket on the 0 so that we include 0 in the range. So notice that I am not touching the graph in this middle section here. So from 0 to 3, I am not touching the graph. But then when I get to 3, I'll be touching over here, and I'll be touching over here. So from 3 all the way up to infinity will be included in my y values. Now, for 3, I want to decide whether we're going to use a parenthesis or a bracket. Now, what I said about these lines is that these lines get closer to the horizontal line without ever touching it. So because they never touch it, 3 is not part of the range. So we're going to use a parenthesis on the 3 because it never gets reached. So we've got, let's just repeat that one more time. So starting from the bottom, I'm touching the graph from negative infinity to 0. 0 is included in the range, so we used a bracket. I'm not touching the graph, and then when I get to here at 3, I am touching the graph, so 3 to infinity, and because we have that dashed horizontal line there, the graph doesn't reach that line, so 3 is not included in the range. So we've got our range being negative infinity to 0, including 0, union with 3 to infinity, not including 3. On this example, we want to evaluate the following function at the values of 6, negative 2, and x minus 2. The function that we're working with is f of x equals x squared minus 1. So let's give this a try. If we want to evaluate, what that means is to substitute our variable x with this particular value. So we're going to evaluate at 6. That means replacing the x with 6. That would give 6 squared minus 1. 6 squared is 36. I'm following order of operations there. So 36 minus 1 would be 35. Then we want to evaluate at negative 2. So that's replacing the x with negative 2. So this gives negative 2 squared minus 1. We'll follow order of operations. Negative 2 squared is 4. Minus 1 gives 3. And then finally, we want to evaluate at an expression instead of a number. So these are both numbers. This is an expression and it has a variable in it. So we're going to replace the x with x minus 2. And that looks like x minus 2 squared minus 1. And when we simplify this time, because our expression has a variable in it, we're not going to get a number answer. We're going to get an expression answer. So we're going to follow order of operations again, applying the exponent. X minus 2 squared is x minus 2 times x minus 2. And then we'll multiply. X times x is x squared. X times negative 2 is negative 2x. Negative 2 times x is negative 2x. Negative 2 times negative 2 is a positive 4. And then I'll just carry down that minus 1 from above. I'm going to combine like terms. Negative 2x minus 2x is negative 4x, and 4 minus 1 is 3. So we get the expression x squared minus 4x plus 3 when we evaluate at x minus 2. For this example, we want to find the center, radius, and intercepts of the circle with the given equation and then sketch the graph. The equation of the circle that we have is x squared plus y squared minus 14x plus 2y plus 25 equals 0. This equation is written in the general form of a circle. And what's more convenient for us to find the center and the radius is if the equation is in standard form. And standard form looks like this: x minus h squared plus y minus k squared equals r squared. Now this format, like I said, is much more convenient because the h and the k stand for the center and the r stands for the radius. So if we can get it to standard form, we're going to be able to identify both the center and the radius easily. It's also could be a little bit easier to find the intercepts in standard form as well. So what we're going to do is we're going to use a technique called completing the square. This square part of our standard form is essential to have it in standard form. So completing the square, this process, will give us these perfect squares in our equation. So to create these perfect squares, we're going to group the x's, group the y's, and move the constant to the other side. So we're going to group these x terms together. We're going to group these y terms together, and this constant we want on the other side. So we'll write this as x squared minus 14x plus y squared plus 2y. And to move that constant to the other side, we have to do the opposite sign. So we get a minus 25 on the other side. Now, within these groups, we need to add a term in order to make this perfect square that we want. We also need to remember that whatever we add to one side of the equation, we have to balance and add the same thing to the other side of the equation. Now the number or term that we add here, I like to call it the magic number. So we're going to find the magic number for the x's. And for the x's, we're going to start with that negative 14. We're going to cut it in half and square it. Negative 14 cut in half is negative 7. And then negative 7 squared is 49. So our magic number for the x's is 49. I'm going to add 49 to the x group and balance the equation by adding 49 to the other side of the equation. Then I need to find the magic number for the y's. So to find our additional term, I'm going to start with the coefficient on the y, which is 2, cut it in half and square it. 2 cut in half is 1, 1 squared is 1. So our magic number for the y's is 1. We're going to add 1 to the y group and balance the equation by adding 1 to the other side. So now that we have figured out the number to add to the x group and the y group, the x group is going to factor to become a perfect square. The y group is going to factor to become a perfect square. That's completing the square. So in the x group, if I try to factor that trinomial, x times x is x squared. 7 times 7 is 49. And if I put minuses here, minus 7x and minus 7x will give me the correct middle term. So my x group factors to be x minus 7 squared. For my y group, if I try to factor that trinomial, y times y is y squared. 1 times 1 is 1. We want to create a plus 2 in the middle, so we need pluses. And that's a 1y plus a 1y is 2y. So that gives y plus 1 squared. On the other side of the equation, we have 49 plus 1, that's 50. 50 minus 25 is 25. So we've now changed the equation from general form to standard form. And with it in standard form, we can identify the center and the radius. As a center of 7, negative 1, with a radius of 5. We can also, from standard form, find the intercepts. How about we find the x-intercept using standard form and the y-intercept using general form, just so you can see it done in multiple ways. So to find the x-intercept, we'll take our standard form, x minus 7 squared plus y plus 1 squared equals 25. And when you find an x-intercept, you let y equal 0. So that gives the equation x minus 7 squared plus 0 plus 1 squared equals 25. 0 plus 1 is 1, and 1 squared is 1. I'll subtract 1 on both sides. That gives x minus 7 squared equals 24. I'll square root both sides. The square root and the square cancel each other out, and I get that plus or minus symbol on the other side. I'm also going to rewrite 24 as 4 times 6. The square root of 4 is 2, and 6 stays inside the radical. I'll add 7 to both sides and get x equals 7 plus or minus 2 square root of 6. And I have my x-intercepts. So then I want to find the y-intercept, and I said I would go back to general form. The original equation was x squared plus y squared minus 14x plus 2y plus 25 equals 0. When you're finding a y-intercept, you let x equal 0. So that gives the equation 0 squared plus y squared minus 14 times 0 plus 2y plus 25 equals 0. So this simplifies to be y squared plus 2y plus 25 equals 0. If you're trying to solve this quadratic equation, I typically will try to factor first. So y times y is y squared. 25 has factors of 5 times 5, but 5y and 5y is not going to give you the correct middle term, so that's not going to work. Okay, well, 25 is also 25 times 1, but 25y and y is not going to give me 2y. And these are the only possibilities I have for factoring. So I'm not able to solve this quadratic equation with factoring. So instead, I can use the quadratic formula. Using the quadratic formula, I would have y is negative b plus or minus the square root of b squared minus 4ac all over 2a. For this example, a is 1. A is always the coefficient of the squared. B is 2. B is the coefficient of the linear term. And C is 25. 25 is the constant term. I'll substitute this into the quadratic formula. That's negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 25 all over 2 times 1. So we'll continue on. We have negative 2 plus or minus the square root of 4. 4 times 25 is 100, so that's 4 minus 100 over 2. Negative 2 plus or minus the square root of negative 96 over 2. And notice that I'm getting a negative value underneath the radical. So this is a complex or imaginary number. So because we're getting a complex number, we know that there is no y-intercept for this example. One final thing is that we want to graph this circle. This will also help verify what we found about the intercepts. So let me zoom out and get a graph on here, get a grid on here. And earlier we found that we have a center of 7, negative 1. So our center is 7 to the right and down 1 with a radius of 5. So I'm going to go up 5, to the right 5, and down 5, and to the left 5, and sketch out the circle. And when you sketch out the circle, you can see that we do have two x-intercepts. Excuse me, I marked that in the wrong spot. Two x-intercepts. And you can see that the circle does not reach the y-axis. And so we have no y-intercepts, confirming what we found just a moment ago, that there is no y-intercept for this circle. Okay, so just thought I'd take a second to review everything. We use completing the square to change the circle from general form to standard form. Once the circle was in standard form, we were able to identify the center and the radius. Then we found the intercepts. And just to show you a variety of approaches, I found the x-intercept using standard form. So we found the x-intercept to be, we had two of them, 7 plus 2 square root of 6 and 7 minus 2 square root of 6. And then the other technique for finding the intercept, I used general form, and we had to use the quadratic formula. And because we had complex intercepts, because we had a negative underneath the radical, that meant we had no y-intercept for this particular circle. So on this question, we're given this picture. We want to answer a couple questions. We want to know for how many values of x is f of x equal to negative 3? How many values of x is f of x equal to negative 3? So one thing to keep in mind is that f of x is the same thing as y. So this means y equals negative 3. You can think of y equals negative 3 as a horizontal line on your graph. So negative 3 is right here. And if I draw a horizontal line at y equals negative 3, that's the equation y equals negative 3. What this is showing me is all of the ordered pairs on this grid that have a y of negative 3. So every single ordered pair on this line has a y coordinate of negative 3. We only want the ones that are on this graph, so we can focus on the intersection points. So we have an intersection point here, we have an intersection point here, and it looks like we might have an intersection point here, but you can see it's drawn with an open circle. And that open circle means that it is not part of the graph. So this one is a no, but these two are yeses. So we have two values of x where f of x is equal to negative 3. Then the second question is, what is the value of f of 4? F of 4 tells us that the x is equal to 4. And f of 4 is a y value. So essentially what this notation is asking us is, what is y when x is 4? So we need to go onto our graph and find where x is 4. This is 1, 2, 3, 4. We find where x is 4. And if I draw a vertical line here, every ordered pair on that line will have an x coordinate of 4, but we really only want the one that's on this graph. So we're going to look for that intersection point, which is right here. This is the one that is on the graph. And that ordered pair would be 4, negative 1. So f of 4 is negative 1. So y is negative 1 when x is 4.
Thank you for checking out my videos. Have a great day.